Hi, I'm Brandon Stewart, and I'm an associate professor in the Department of Sociology and the Office of Population Research at Princeton University. Along with Justin Grimmer and Molly Roberts, I'm the author of the new book, Text as Data, a new framework for machine learning and the social sciences. And in the lecture today, I'm going to talk a little bit about how the book thinks about research design with text as data, as well as the task of taking text and turning it into data. That is, taking strings of text, turning it into numbers that we can use statistics to learn about the insights that documents have to provide us. All right. Hi, everybody. Welcome. So today I'm going to talk a little bit about this book that I'm Brandon Stewart, that I wrote with Justin Grimmer and Molly Roberts. And so this is the nice cover of the book. Feel free to check it out. We're going to talk a little bit about some of the core ideas. And I'm going to start today with just a little bit about how we think about research design in working with text as data, and the basics of how we represent text as data, which then gives us the ability to sort of move on to doing other cool things, which Justin will talk about next. So I want to start with two closely related claims. So the first is that for much of its history, scarcity has really defined empirical work in the social sciences. And what I mean by that is scarcity of data, scarcity of computation, scarcity of time to think, like great social science thoughts. And now we're in this era of abundance. There's so much data, there's so much computation, and there's so many more cool things that we can do to bring these elements to our research design. And particularly, this is going to change how we think about approaching that research design task. So what this comes together is we think about this as now we're coming into the age of custom measurement. So what do I mean by that? Well, the quantitative turn in 20th century social science was really driven in many ways by shared surveys, which sort of actively solicited information from people. So things like the American National Election Study or the General Social Survey or the Panel Study of Income Dynamics are these sort of large repositories developed by teams of academics asking lots of different questions that were trying to support many different research agendas. Right? So if you wanted to work on something, you sort of found whatever the closest equivalent was to a question that helped address your concerns on, say, the General Social Science Survey, and then you worked on it, right? And so the situation that we're in today, though, is there's been this massive increase in unstructured text. And then the communities now leave these digitized footprints that we can passively measure. Right, so the difference between the active and the passive here is that for the ANES or the GSS, we have to think about what question we want a priori, and then actively go and ask people about that. Whereas by contrast, when people are just writing things on Facebook or Twitter or even in op-eds in newspapers, right, we're getting their choice of what to share. And that allows us to sort of go back after the fact and say, hey, this cool event happened that we weren't anticipating. Let's go back and see what people were saying before that event. And so all of these additional data sources have led to new methods to deal with them, new approaches to text analysis, new approaches to network analysis. And that has led to the possibility of creating custom measurements. That is, measurements that weren't designed by a large group to pick up lots of different research agendas, but were designed by individual researchers to really go in and understand their own particular research project. And there's a lot of considerations to be had in this. So we have to be concerned about representativeness, right? Whether or not the data that we have is reflective of a population, concerns about validity and replicability. These are all the common concerns that we always have, but the important thing is that this moves from a community consideration in the context of the ANES or GSS, where there's a bunch of different academics that are working together to ensure that these things hold, to a more individual task, where you've developed a measurement for your particular study, and so ensuring that all of these criterion hold sort of fall on you as an individual researcher. And so we think about three major themes for thinking about doing research in this new era of abundance with all these new measures and data. So the first, as Justin Grimmer sort of notably wrote in a nice essay, we're all social scientists now. We need sort of problem-driven, theoretically motivated research in order to understand human behavior. It's not just going to like pop out of the data by itself. And this is ultimately going to be team effort, right? It's going to be a combination of social science, but also computer science and statistics. It's sort of a fundamentally interdisciplinary exercise. The second theme is that this is a kind of quantitative research that's fundamentally qualitative in interpretation. So what I mean by that is that like we have to like read to really carefully validate what's going on in text analysis. There's always this sort of humanistic interpretive exercise that's happening as part of text work. And so that's what I mean when I sort of say it's like fundamentally qualitative. It also means that like expertise in the topic area really matters, right? You have to know something about what you're doing the text analysis work on in order to be able to interpret and understand the kinds of analyses that you're running. So the third theme is that science is, in our view, really sequential. So discovery and induction are not bad words. They're just like a part of the process that we historically have not talked about very much. And science, and when you look at it this way, it's like sometimes accidental, right? We stumble into research topics that we weren't necessarily anticipating, often by like really like incidental means. And that makes us sort of question, like, can we innovate on this process of discovery? Can we come up with methods that are going to help us discover better things faster? Right? It certainly seems possible, and in order to start that process, we really need to talk about discovery as an essential part of the research enterprise much, much more clearly. So this is all by way of saying that we need to rethink the conventional approach to doing research design. And really that's, in many ways our book is about text analysis, but more broadly, it's really just a way of thinking about research design that's applicable to all kinds of areas of machine learning and computational social science. So one of the figures that we have in the book that we talk about a fair amount is this chart sort of depicting what we think of as the deductive model, which is the way that social science is generally taught. I'm actually not even sure it's the way it's even practiced, but it's the way we talk about it being practiced. And then is this very linear, you start with a theory or model that comes from the ether, you derive some hypotheses, you do some data collection after your hypotheses, and then you analyze and you look at results. And our argument is that no, like really what is happening in practice and what we ought to be doing is something that's a little bit more iterative. That theory ultimately comes out of a data, like the data generally, which then informs more data collection, which leads to more analysis. And it kind of goes in a little circle until at some point it straightens out. And what's really important in sort of understanding this is that it's really, really helpful to have this data collection and analysis that comes after the hypothesis. That's the part that the deductive model gets right, that it is actually useful to have some data that you haven't seen before developing your hypotheses. But if we pretend that everything is deductive, while our best ideas come from the data, we're not doing ourselves any favors, right? Instead, what we need to do is develop methodological practices that make the most of this iterative process. Okay, so there's a lot of that could apply to things beyond text analysis. And so in sort of shifting into the just text analysis part, I want to talk about what text methods can do. And I want to start with this metaphor that comes from Hopkins and King. It's the haystack metaphor. Okay? And the whole idea here is that there's a notion of like, we're trying to improve reading. So we can think about like a strand of hay that like interpreting a single sentence for like meaning or theme or understanding is like analyzing a single straw of hay. And humans are really amazing at this, right? Like you think about analysis of poetry or Straussian political theory or something, right? You can get a lot of depth out of like one beautifully crafted phrase. But computers really struggle, right? It's hard to sort of get a ton out of just like a single line for a computer. But that's actually not often what we're trying to do in social science. We're often trying to compare and organize and classify text. And we might think about this as like compared to analyzing a single strand of hay. This is the task of like organizing the haystack, right? Counting all the, the hay, putting them into little piles. And this is the kind of thing that humans are really terrible at, right? We have extremely tiny active memories, which makes it very hard to hold like a large number of categories in our head at the same time. And computers are amazing and getting better all the time. So if what text methods do is help us compare and organize and classify text, let's think about like what they don't do. So they don't like tell us any underlying truth about a document. There's no like grand unified theory of language here that says this is the one and only right way to interpret a text. They don't, importantly, replace the need to read, right? This isn't computer automated reading. This is computer assisted reading. This is like amplifying what a human can do, but the human still needs to be doing some of that reading and interpreting. And importantly, it's not going to develop a single tool or evaluation that's going to work for every task, right? Ultimately, there's tons of different things that we can do with language, and we're going to need different tools and different styles of evaluation for each of them. So this is all my way of saying that text data needs a great question and assumptions, which we might think of as like coming from some theory in order to produce insight. So broadly speaking, there's a few different types of methods for different goals. So there's supervised learning, which is like pursuing some known goal. So sort of programmatically, we can think about this as like a human goes in and annotates a subset of documents for some categories. And then the algorithm sort of picks up on what the human is doing and annotates the rest. And so this is the highest effort comes before you ever run the model. It comes in doing that initial annotation and determining what the coding scheme is. A second approach is unsupervised learning, where the goal is sort of to learn what the goal is. Here the idea is that the algorithm discovers themes or patterns in text, and then humans come in and interpret what those patterns might mean for social science. And there, the highest effort comes after we run the model. So importantly, both of these strategies are augmenting rather than replacing human effort. They're just bringing it in different parts of the process. And both need to be sort of very carefully validated, because neither is sort of like obviously a priori right or better. And these are the two sort of areas that Justin will talk about next. Okay, but I'm going to start by giving an example of a piece of text analysis that actually goes back a bit in time. So this is a 1963 paper that was published in the Journal of the American Statistical Association by Frederick Mosteller and David Wallace. And it's about inferring the authorship of the disputed Federalist papers. So here's the core problem setup. And we're going to talk about this because even though it's older, I think what you'll see is that it works because of the nature of the research design and not because of like the fancy methods they're throwing at it. Okay, so the Federalist papers are these 85 essays that were published anonymously from 1787 to 1788. And authorship is pretty well established for 73 of them because there's essentially no competing claims over authorship. So Hamilton wrote 51 of the essays, John Jay wrote 5, Madison wrote 14, and Hamilton and Madison jointly wrote 3. But there's another set of 12 essays where there are disputed claims. Both Madison and Hamilton claimed authorship at various points for those papers, and because they were originally unsigned, we don't know for sure who wrote them. And so the core strategy that Mosteller and Wallace, who are statisticians, are going to take is to infer authorship based on relative word frequencies. So here's essentially the setup. They're going to count word frequencies of function words, words like by and from and to and upon, and in the sort of set of essays that have undisputed authorship, the ones where you didn't have competing claims. And then we're going to collapse the author-specific rates of using those different words and model them with Poisson and negative binomial distributions. Then, because we have a sort of assumed data generating process for these words, we can just use Bayes' theorem to back out the posterior probability that Hamilton or Madison wrote each disputed essay. And so the key idea, like the core thing powering this, is that for words like upon, it provides some insight into style that might tell us something about the author, kind of regardless of the content of the piece. So we're not trying to say, oh, like, Hamilton wrote about this aspect of federalism a lot, and consequently we think that this unsigned paper was written by him. We're using these cues of sort of style and writing. And so Mosteller says this really nicely in his autobiography. He says, we want words whose use is unrelated to the topic and may be regarded as reflecting minor or perhaps unconscious preferences of the author. Right, so again, this is like a very specific design choice they're making. Now, this was all done in the 1960s, and so it was complicated. So this is a picture of an IBM 7090, which is the kind of computer they actually ran these analyses on. And they have that, Mosteller has this great story in his autobiography about how they cut all the individual words on little slips of paper, and if someone would like open the door, all the slips of paper would go flying around everywhere, right? And so this was just hard. This is like what we mean by scarcity, right? There's just not, when your computers are that giant, there's less computation to go around, and so you have to think much more carefully about exactly like what are we modeling. As a side note, when we talk about issues of happenstance in discovery, Mosteller has another fun description in his autobiography where he talks about, he says, when I worked at the Office of Public Opinion Research, I got to know Frederick Williams, a political scientist. One day in 1941, Fred said, have you thought about the problem of the authorship of the disputed Federalist papers? I didn't know there were Federalist papers, much less that Hamilton and Madison had claimed authorship of them. So this is like sort of a fun, like, hey, like interdisciplinary collaboration can lead to interesting kinds of problems. Okay, so that's this was all done, again, some time ago, but the problem's been studied a lot since. They found originally that there was extremely strong evidence that Madison was the author of the 12 disputed essays. And since then, a number of researchers have analyzed the same data with like much fancier methods and gotten very similar results. In other words, like, this isn't really a story about like the particular technique or their choice of distribution or statistical method. It's really just a story about they found the right cue of authorship information in these texts, and then we're able to exploit it. So thinking about problems like this gave us the opportunity to think about like principles for research design with text overall. And so in the book, we talk through 6 different principles for thinking about how you do research design with text, and many of which I've sort of already hit on, that theory is like an important starting point for analysis, that we're about augmenting humans and not replacing them, the sort of iterative and cumulative nature of science. And one thing that I haven't hit on as much yet, but is extremely important, is this 6th point, that validation is really essential. That the results of these methods aren't justified because we applied a particular method, and this method, always gets the right answer or something like that. They're sort of powered by the validations we do to demonstrate that this is a feasible strategy. Okay, so the book itself is really organized by tasks rather than by methods. If you pick up a machine learning textbook, often what you're going to find is, maybe there's a chapter on kernel methods, there's a chapter or 8 chapters on neural networks, and there's a chapter on linear models, that kind of thing. And we chose not to set things up that way. We wanted to organize based on what you're trying to use these methods to do. So we have a section on discovery, right? That is the sort of sparking new concepts and exploring the data in different ways. And again, the logic here is that once we acknowledge that discovery is a key part of every social science project, it becomes more possible to develop methods to improve discovery. We have a section on measurement. That is like how you go about operationalizing a concept and then measuring those phenomena at scale. And then finally, we have a section on inference with a particular focus on causal inference. And that is like assessing the effect of some counterfactual intervention into the world. And there, we've thought about text playing many different roles, such as the treatment or the intervention that we're making in the world, as the outcome or measuring the result of the intervention, and as a confounder. That is the thing that kind of makes observational studies what they are. So the first thing, though, before we can do any of those tasks, and what I'll talk about in the rest of this lecture here, is representing the text numerically as data. And I'm going to start with the sort of first recipe for representation, which is called the bag of words approach. And this is just one of many possible ways of doing bag of words work. And bag of words is just one of many possible representations we can use for text. And I'll talk about some more at the very end. But it's a useful one, and it's a way of retaining just very coarse, strong signals in the text. So what are we going to do? We're going to go through the text, and we're going to remove a bunch of stuff like capitalization and punctuation. We're going to discard word order, and this is where the term bag of words comes from, right? It's like the idea of like we took a text and we like broke it into words and we threw it in a bag and shuffled it around, right? Like the idea that we're not preserving the sequences that is how we normally engage with text. We're going to discard stop words, which are things like of or for or to or from, those kinds of function words that were actually the primary focus of Mosteller and Wallace's study. We're going to create equivalence classes of words where we collapse things, generally by stemming, which is sort of just hacking off the ends of words. So taking like run, runs, and running and mapping them all to the same token. That's a way of sharing information. And then we're going to discard often some less useful features. And this really depends on the application, but is often the nature of language is such that you're going to have tons of unique words that only appear once in the text, or maybe twice or 3 times. And there's very limited amounts that we can learn from those very rare words, and so we'll often drop them. And there can be other reduction and specialization on top of that. So the output then is for every document we get a count vector, and each element just counts the occurrences of the stems. So it's how many times did some version of run show up in this particular document. And that's a really simplistic interpretation of what's going on in the text, but shockingly, it's still going to be able to do a lot of work for us. So let's step through this recipe little by little. Obviously the best way to do this is to practice, right? And do it yourself, but I'll sort of walk through a little bit how it looks. So the implicit first step in these things is always splitting the document into individual words. And this is a process called tokenizing. And in many languages, tokenizing is really easy, English being one of them. You mostly just split on white space. So when there's a white space, you say, hey, it's a different word. This isn't always as easy. So Chinese and Japanese, for example, don't have spaces between words. And so we end up needing a word segmenter to sort of break the words apart. But even if the words are easy to split, there's sometimes compound words that we want to leave together. So for example, we might believe that White House means something so distinct from white and house that we want to treat it as one unified token. And there's 2 kind of broad strategies that people use for dealing with these compound words. They either leverage linguistic patterns, so things like, hey, if there's like adjective-noun combination, that often indicates some kind of compound word. And the other is statistical testing for collocations. So basically, do white and house appear together way more often than you would sort of expect by chance if they just showed up independently. And when you see that pattern, you might go, well, that might indicate that there's some special meaning to White House that we need to think about. The second stage was around stop words. So these are, in English language, they're just sort of like placeholding words that serve some functional component, like the or a or at. And we can think about them as sort of adding noise to documents without conveying a lot of information, particularly a lot of information about the topic. Now, in the context of Mosteller and Wallace's study of the Federalist Papers, it conveyed a lot of information about the author, right? And this is where us as researchers have to think very carefully about the design component. Like, what kind of signal are we trying to pick up from the text? So we often discard these stop words so we can focus on the sort of usual substantive words. But as I mentioned, we got to exercise caution when doing this because we might lose something that is of primary interest to us. Ultimately, you may need to customize your stop word list. A common reason is because there's some like common footer on text, or there's something about the way you selected the text that there's some word that's fundamentally uninformative. So the next stage is to create an equivalence class of words, and this just helps us take the very high dimensionality of maybe hundreds of thousands of unique words and map them down into something a little bit smaller. And so the idea is we're going to take all words that we think refer to the same basic concept and group them together. So family and families and familial all have this common stem, right, and we think might reference a common idea. And so stemming and lemmatizing are two ways of getting at this. They're basically just many-to-one mappings that take us from the space of like all of these different variants of a word down to the common form. So stemming is like a really simplistic way to do this. You're basically just hacking off the end of words. I mean, it's a little more nuanced than that, but not by much. And there's lots of different ways to do this that are implemented in sort of all the major packages. This is a very common strategy. Another approach that can be slightly better is lemmatizing. And here what we're going to do is we're going to condition on the part of speech, like whether or not it's a noun or a verb or something like that, which is going to help us work out what the kind of dictionary form or the lemma of the word is. And what's nice is that lemmatization sort of verifies that the result is actually a word, right? Like if you kind of go back here, right, the thing that family, all these variants of family maps to isn't actually itself a word. But lemmatization will do that for you. But the key idea in both of them is, again, we're just creating equivalence classes. We're just saying, for our purposes, for our analysis, we're going to treat all these different variants of family as the same. Okay, so let's just run a complete example using some example sentences that happen to include the word manufacturing from a corpus of State of the Union addresses. So the first thing that we might do is combine certain words together to improve the inference. So here we might think that United States is a particularly important word pair. And so we add just like a little underscore here in this setup so that will get treated together and won't get split apart. We can then just lowercase and remove punctuation and stop words. And again, this works if like what we're trying to capture is something like the topic or maybe the sentiment of the text. But it certainly makes the text immediately less readable. And we might lose these kind of stylistic signals that if we were interested in that kind of task, we would want to keep. Then we start hacking the endings off words. And so now, again, to the human eye, this is just getting even less readable, but it's getting even more simple for the human to understand. And finally, we can just count all these things up and plop them into a matrix. So this is a tiny matrix because there's only 2 documents. But you can see with even only 2 sentences, already the matrix kind of runs off the page, right? And a property of these matrices is they're going to be big and they're going to be sparse. And by sparse, I mean that a lot of the entries are 0. Most documents don't contain an instance of most words. That's going to be useful for computational reasons, but also it's just like a useful property for thinking about the kind of information we have access to here. So one question is like, how could this possibly work, right? How could this horrifying reduction of our original sentences be useful at scale? And there's sort of 3 answers to that. So the first is, fundamentally, it might not. And this is why validation is so critical and task-specific. We need to know that the kind of signal that we want to recover with the text is actually recoverable. So we need some additional way to just check that what we're doing makes sense. The second is that there is a central tendency in text, that words often imply what the text is about. So, war, civil union, consecrate, dead, died, lives are all like words from like the Gettysburg Address, and like it gives you a feel of what the document is about, like just by virtue of seeing those words in isolation. And words once used are often repeated in documents in a sort of property that's often called burstiness, which helps to create a theme for what the article is about. And that theme is often part of what we're trying to extract with text analysis. And then finally, human supervision can help. Like using human judgment or human coders can help methods identify subtle relationships between words and outcomes of interest. The strategy that was used by Mosteller and Wallace for understanding the Federalist Papers, they were counting function words in part because they didn't have a nice software like Spacie or Quantita to do the counting for them. They had a bunch of assistants literally cutting out strips of paper. But it also is important because it wouldn't actually have worked as well without them identifying those key function words, because there would just be too many words, and there would be too many like chance differences across those different kinds of words. So this is also all to say that it's easier to capture some things than other things. So text analysis is really good for answering questions like, what are these documents about? Or roughly what sentiment do they have? And it's a little bit harder for things that are closer to that analyze the strand of hay, get like deep meaning types of questions. So once we have a nice matrix of all of the different documents and all the counts of the words, we can start applying kind of rich results from other areas of statistics and math. And so a thing that we often do is apply what's called a vector space model, which is that we assume that what these sort of count vectors are giving us is vectors in a space. And this is going to allow us to leverage this rich set of results from linear algebra. It's going to provide like a geometry of what it means for different texts to be related to each other that we can then go in and say modify with different kinds of word weighting. It also provides very natural notions of distance. And often this idea of like how close are 2 documents to each other is the fundamental thing that's going to power all the kinds of methods that Justin is going to talk about when he talks about supervised learning and unsupervised learning. That implicitly or explicitly, those all rely on being able to say, what does it mean for 2 documents to be close to each other? And that's what is sort of at stake in creating a representation, right? It provides a notion of what it means for documents to be alike. So I mentioned that one thing that we can do is instead of just using the raw counts, we can weight words in some way. And there's lots of different ways to do that, but I'm going to mention one because I think it provides actually a really nice like linguistic intuition of what is valuable. So this starts from thinking about what properties do words need to effectively separate concepts. Well, basically, they have to be used frequently. If a word isn't used often enough, it can't help you organize your corpus in a meaningful way, because it just doesn't show up enough to tell us anything. But it also can't be used too frequently, right? The word the or from is used incredibly frequently, but it actually doesn't separate very much. Even in the Federalist papers, words like the and from aren't the ones that really separate Hamilton from Madison, because everybody's using them at approximately the same rate, even though the rate is really high. So, a simple example, if we are analyzing statements about Donald Trump and they all contain the word Trump, then this is going to add very little to similarity or dissimilarity measures. It doesn't really help us sort of move forward our analysis. So what we're going to think about is a weighting that tries to find those words that are used frequently but not too frequently, a kind of Goldilocks weighting, right? Trying to find the thing in the middle. And so it's going to have two components. There's going to be a term frequency component, that is the count of a word in a document, and an inverse document frequency weight, which is just the natural log of the corpus size divided by the number of documents in which the word occurs. And so what this is just going to effectively do is it's going to, words that are used frequently are going to get counted with that term frequency term. But then we're going to sort of upweight words that are rare in the corpus overall, which is what's happening in the inverse document frequency term. We just kind of multiply those together, and we get a new weight for the word. And this is a surprisingly robust heuristic. So I would completely understand if at this stage you're thinking, hey, this seems way too simplistic to do anything useful, right? All we're doing is counting up some words. Maybe you've seen even fancier language models and you're thinking, why isn't he talking about those? And I will briefly in a minute. But I want to make the point that this very simple recipe can actually do surprisingly well, which has a lot to do with the fact that as humans, we're not quite as good as we think we are at assessing similarity between things. So let me tell you a little story about a project that Justin worked on. So this is a book called The Future of Political Science that was edited by, among others, Gary King. And Gary and Justin did this kind of interesting project when they were putting together this book. So the book has 100 different essays from all these different people, very short essays about what the future of political science is. And so the problem when you have 100 different essays is that you have to organize them in some way, right? You have to figure out how to order them in a way that's meaningful to read. And so Justin and Gary were okay, they were messing around with text analysis methods. They're let's just try this with text analysis. And the thing I want to draw your attention to on this ad is just this bit down here that says the organization of the essay strikes me as nothing less than brilliant, okay? So how did they get to nothing less than brilliant? All right, here's what we're going to talk about. So they have this nice figure in the book that, I'm sorry, it's a little tilted. But basically what they did was they used this recipe, right? They counted up words, they weighted words, and they just looked at the sort of distance between documents to sort of assess which documents are closer to each other. Now, again, remember, these are essays from leading experts in political science pontificating about the future of an academic field, right? And all they've done is just coarsely counted up some words and said, hey, where's there some overlap? Now, understandably, some of their colleagues were skeptical about this organization, and so they decided, well, we're going to go in and we're going to do a test, we're going to do a comparison. And so they had one team at one university make clusters of documents. And so they put them into categories like the ones you see here on economic equality or gender equality or political equality or culture. And then a different university, a different faculty member instead of graduate students, went in and for every document they said, what's the closest document of all the other 99 to this one essay? So we can link them up in this way. Okay. And then Justin and Gary went in and they said, okay, let's run a test. Let's see who has the best organization. So what was the nature of the task? Well, the task was, let's find documents that are similar to each other. And so they said, okay, let's just go in and test that. And so they ran an experiment to have the humans compete against the machines. And so they had humans look at a pair of documents that were matched together by some procedure, okay, and mark whether or not it's unrelated, loosely related, or closely related. And then they just averaged those scores. And so the higher numbers would suggest that that pair is a better pair, right? It's more similar along things that the humans thought were important. And so as a simple baseline, they did pairs based on random selection, right? So these are only similar insofar as they're like similar by chance. And of course, all these documents are like somewhat similar because they're all about the future of political science. And you can see that the scores reflect that, right? The overall mean is 1.38, which given that 1 is the minimum, is quite low, right? It's assessed that these random pairs are not very good at being similar. So then there were the hand-coded clusters. So this was the team of faculty and graduate students who said, yes, we're going to find the clusters of documents that best describe this corpus. And you can see they did like a little bit better than average, right? Or than the random selection, but like not by much, right? So it's like a little bit. So then we go to the team of people who picked the best match, like the single best document that matches a given essay. And here you see like a substantial jump, although the average is still hovering right around the area of loosely related. And then, as you won't be surprised because I'm telling this story, the machine just crushes them, right? Just does just a big jump even better of getting like these more tightly related recommendations. And what's particularly clever about this story and why I love telling it so much is that these evaluators that are off to the side here in the table, these are the actual hand coders who created the first clusters, right? So these people implicitly agreed that the machine, this like very coarse signal of text, had done a better job than they had of organizing these documents about the future of political science. So it's not that these things are always going to work, but hopefully this is just like, it's a cute small-scale experiment showing that it actually can work even when you have this very loose signal. Okay, so the last thing I'm going to talk about is the next step beyond this simple bag of words setup. And that's using the idea of word embeddings. So the kind of feature representations that I've shown you thus far, these like counts of words, are atomic in the sense that every word is encoded as what's called a one-hot encoding, right? So what I mean by that is every word to the algorithm is completely unique from every other word. It's part of why we do things like the stemming and take like family and families and familial and collapse them into one. It's a way of telling the algorithm, hey, these things are all related. But otherwise, it doesn't understand any word as related to each other. So, kitten and cat are the same level of related as cat and truck. Right? And so with infinite data, with infinite labeled data or even unlabeled data, this isn't a problem, right? We can learn the unique relationships between all the different words that we have access to. So we can learn how cat is related to kitten or cat is related to truck. But we often are in a situation where we have limited data. So it's say hard to learn that politics and political are related without having a bunch of instances of those words. And that's part of why we did the stemming, right? So that we knew that politics and political were related. But the problem is that stemming isn't going to do anything for you with words like, say, hotel and motel. right? Even though we know that they're very closely related. And so word embeddings are going to be a way to bring that information in about the relationship between words. So here's the breakthrough insight that powers it. It's what if we could learn a distributed representation on a large unlabeled set of data that could then be useful for other context-specific tasks that use different data. So in other words, what if we could use all the writing on the internet to help us learn that hotel and motel are sort of related to each other? And we do this by placing all words in a lower dimensional space. Now, it's not super low dimensional. Often these things are 300 to 500 dimensions. And that's a pretty big space, but it's really, really small relative to the hundreds of thousands of dimensions that are often used in word counts. And so I don't think ex ante it's super obvious that this will work. But it turns out it does for lots of tasks, which is super interesting. And the reason why, or at least the reason that we think why, has to do with this idea of the distributional hypothesis, which linguist David Firth sort of has this pithy quote that you always have to give this quote when you're teaching word embeddings. It's like an iron law. You shall know a word by the company it keeps. And part of why everyone quotes this is because it is just such a beautifully simple instantiation of what's going on here. That we know what a word means because we know how it gets used around other words. And so the way that we're going to operationalize this is we're going to represent the word based on the words around it in a small context window. So here's, for example, a bit of a sentence that comes from Goffman's presentation of self. And so if we're interested in understanding the word show, we might look at all of these words that are around the word show and lots of other contexts where the word show is used. And that's going to give us some signal about what show might mean. And so this, in sort of the modern era, we might say this gets first really it's not really first introduced to the literature, but what's first sort of prominent outing in the literature comes from this work by Mikolov et al. That propose essentially two broad strategies. We predict the focal word show given its context, or we predict all the context given show. So in other words, we either predict this thing in blue given all the words in gray, or the other way around. But either way, it's a prediction problem. And both these algorithms are broadly called word2vec after the software that implements them. There's another quite prominent strategy called GLOVE, which stands for Global Vectors, by Pennington et al. And this works through a similar kind of predictive logic. It's basically just a dimension reduction of co-occurrence counts within a window. But the core idea is the same across both, right? We're just looking in a little window around a word and trying to understand what other words show up there, and using that to help us learn about what the properties of that word are. Right? We can learn that hotel and motel have a somewhat similar meaning because there's a lot of words that show up around it, like check-in and baggage and rent, right? Room, for example. So I want to just give just the tiniest concrete example so you can see why this works and why it's going to give us some really useful leverage. So imagine we have this incredibly simple two-dimensional space, and we have three words, cup and coffee and tea. Okay? And we hit our first example. I had a cup of coffee this morning. And let's say we're updating the word coffee. And so we are using a window size of 2 here. You're always sort of picking how far around this word are you looking. Here I'm using 2 as an example. This is way smaller than people typically do. Okay? And we see that, hey, the word cup is in there, right? It's in that little window. And so what that's going to do is it's going to take coffee, and it's going to move it up there a little closer to the word cup. Right? So then we go to our next example. I had a cup of tea this afternoon. And perhaps we're updating the word tea. And so we move tea up over by coffee. up over by cup. And this, of course, is the key. I was jumping ahead of myself there, is that in moving tea over to cup, we also move it over by coffee, right? And it's like a simple idea, but it's actually like key to the whole enterprise. So the thing that is powerful about word embeddings is that they offer this property that Jeff Hinton calls automatic generalization. That is, when we update our understanding of just one word, we affect our knowledge of all the related words. When we come to understand something about coffee, because we see it in our task-specific label data, we also learn something about tea because our word embeddings know that tea and coffee are in a very similar place. Now, that works really well if the meaning that is captured by the word embeddings aligns with the kind of meaning we're trying to extract. And it's, rather problematic when it doesn't. That's the problem with borrowing information from somewhere. It's only as good as where you're borrowing it from. But the idea is that two words with the same embedding location sort of broadly mean that the words in their local neighborhood are the same. The reason that coffee and tea end up with similar embeddings is because they get surrounded by similar types of words in large corpora of text. And so the nice thing about embeddings is that this is a really efficient way of sharing information. So if we learn that cat's related to a concept, it tells us how kitten is also related to that concept, because we learn something about the relationship between cat and kitten. But actually, what's really cool, and this is the thing that I think would have been hard to anticipate before word embeddings took over, it's actually not just things like cat is related to kitten, but it's actually more complex semantic relationships that get encoded in these embeddings. So we might learn that foreign dignitaries visiting France often meet in Paris, and that might tell us something about how foreign dignitaries visiting Spain often meet in Madrid. Because it turns out that we haven't just learned that Madrid and Spain are related and that Paris and France are related, but that they're related in the same kind of way. And that's the part that's like super cool and super powerful, and I think made these things really capture people's attention. Now, note the key here is that the embedding dimension doesn't really mean anything. It only means things in relationship for how these words are related to each other. That's the entire thing this is encoding. So it might have like some very large, three-dimensional vector of numbers, and that vector of numbers like doesn't mean anything by itself. But the pace of computer science marches onward, and the paper that I mentioned was, 2013 back here. And I mentioned, as you can see from the Hinton citation, these ideas go back a long time to the 80s. And so the pace marches forward. And so there's now kind of newer methods that are powered by, again, that abundance of data and the abundance of computation. And the way this has been generalized is to take the idea of predicting a word in a sequence and generalizing it to increasingly complex models. And so this leads to large predictive language models like BERT or GPT-3 that you may have heard about or seen on Twitter or interacted with in some other way. And they also provide distributed representations of sequences of text, much like word embeddings. But because they're looking at a sequence when figuring out the position in space, it allows them to be context specific. So the word embeddings are still a fundamentally bag of words logic. It's just word by word. Whereas these larger language models are doing this prediction task, but with more attention to the order of the words. And that's going to allow them to capture something a little bit richer at the cost of needing just a whole lot more parameters. Now, the thing that's really cool is that some of these models can also generate realistic text. So they're valuable for the same reason the basic word embeddings are valuable, that they provide this embedding that gives us a notion of similarity. Right? You think back to the task that Justin and Gary were engaged in of trying to figure out which two essays are alike. They were just using simple word counts. But if they had used regular, like static word embeddings, like the original word embeddings, which didn't exist at the time, They could have done things like share information across related words. So maybe somebody used a particularly unusual word in only one essay, but some larger corpus of text could have told us how it related to all the other words. That would have been potentially valuable. What these get us is the ability to think about the sequence of the text. It, in some ways, gets a little bit closer to analyzing the straw of hay. Now, what's cool is because these things are fundamentally predictive, though, they can generate realistic text. And so here's where I just got really lazy in the slides, and I said, well, what if I just had this write the slides for me? And so I said, just like I gave it the prompt, can you explain large language models for an audience of computational social scientists? And the model, this is GPT-3, wrote, a large language model is a machine learning model that is trained on a large amount of text data. The model is able to learn the relationship between words and phrases in the text data and can generate new text that is similar to the training data. Large language models have been used to generate realistic sounding dialogue, generate new poems, or even create new works of fiction. So those are pretty good sentences. I remember the sort of first time that I encountered this kind of language generation, and I was like, oh, that is really something. And I think that this is going to be a big space for computational science moving forward, social science moving forward, is how do we make use of this language generation technology? Because this is just another form of abundance, right? It puts on the table a capacity that we didn't really have before. We had the ability to analyze text, but not really so much the ability to generate the text. And with the ability to generate comes like a lot of new possibilities. But again, this is where the elements of research design and validation are so important. Is as GPT-3 itself so acutely notes, that when it's generating new text, it's generating text that is similar to its training data. And these models were trained on data from the internet. And I don't know if you ever have been on the internet, but the internet is a really terrible place that has some terrible people. And so these language models also embed all of that as well. They embed the good and the bad of all the language that is happening. And so they're kind of interesting, like social cultural artifacts that might be useful objects of study in their own right. But when we're sort of using them, it's important to remember that this doesn't know anything true about language. It's just as Emily Bender and Tamik Gebru and others have sort of acutely put, are basically stochastic parrots, right? It's just sort of repeating the kinds of patterns that it's seen. But that is still a very powerful thing that can be very useful to us in social science. So that is to say that they represent meaning sort of based on the data they're trained on. Okay, so that's what I've got. That's the setup for representation, and more information here, and methods I've developed include the structural topic model, which we'll talk about a little bit later. But that's what I've got for you on representation, and I'm happy to take any questions. Thanks. I hope you enjoyed that lecture. We talked a little bit about our approach to research design in text as data, and how design is really an essential part of what we're doing when we're trying to learn about the social sciences. We also talked about representation, how text is this incredibly complex object, and we need to ultimately extract some really basic ideas about it in order to turn it into numbers. And the key I hear is that we can extract lots of information from that text, but we need to choose things that are right from our task. There's so much more to learn in text as data, and I hope you'll check out our book to learn a little bit more.